Hello everyone, I'm Dr. Mohammed Zamri. Let's jump right into our masterclass on electronic instrumentation. Over the next few minutes, we're going to cover the entire landscape, from the very basics of measurement, all the way to the critical skill of error analysis. This is the professional toolkit you need to actually trust your data.
So where do we even start? Well, to master any field, you have to go back to the beginning, to its core principle. So let's ask, what is instrumentation?
You know, you can think of it as having a conversation with the physical world. First, we have to listen. That's measurement. We measure things like temperature, pressure, or voltage. Then we respond based on that information. That's control. This back and forth, this dialogue is really the heart and soul of instrumentation. And this feedback loop right here is the engine that drives everything. You can see how the red elements are constantly measuring, feeding information to the black control elements. Now, for our purposes today, we're going to focus squarely on the measurement side of this. Why? Because without accurate data, any attempt at control is basically impossible.
Okay, so not all instruments are made the same, right? We actually classify them based on a few key things: their fundamental working principles, the techniques they use to get a result, their signal types, analog versus digital, and their specific function. Understanding these categories is really the first step to picking the right tool for the right job.
But here's the big question. How do we know if an instrument is telling us the truth? What actually makes a measurement reliable? The answer is all in its performance characteristics. The easiest way to think about this is like taking a photograph versus shooting a video. Static characteristics are like that still photo. They show us exactly how the instrument performs when everything is calm and stable. Dynamic characteristics, on the other hand, they're the video. They capture how it responds to rapid, real-time changes.
So why this obsession with the static side of things? Because in engineering, trust is absolutely everything. You can't possibly rely on a measurement in some chaotic, dynamic environment if you can't even trust it when everything is perfectly still. This is the bedrock. It's the foundation of all reliable instrumentation.
But here's the thing. Even the most reliable instrument isn't perfect. And this brings us to an unavoidable reality for every single engineer: measurement error. As an engineer, your goal is not to achieve the impossible. You will never completely eliminate error. Your goal is to become an error detective. You have to understand it, you have to quantify it, and you have to account for it in your final analysis. Now, when we talk about these static errors, they tend to fall into three main buckets. First, you've got gross errors. Honestly, think of these as simple human mistakes, like just misreading a dial. Next up, systematic errors. These are consistent, repeatable inaccuracies, like a miscalibrated scale that's always off. And finally, you have random errors. Those are the unpredictable little fluctuations, the noise in our measurements.
Let's dig just a little bit deeper into those systematic errors. They can come from the instrument itself. Maybe it has a calibration problem. They can also be environmental, caused by things like the temperature or humidity in the room. And finally, they can be observational, coming from something as simple as parallax error. Looking at a needle from the wrong angle.
Okay, that's enough theory for now. Let's get our hands dirty and see how this all plays out in a real-world lab scenario.
So picture this. You're in the lab. Your trusted voltage source is set to a perfect 10 volts. You know this for a fact. But you look down at your multimeter and it reads 9.2. What do you do now? How do you professionally and scientifically quantify this difference?
Well, our first step is super simple. Calculate the absolute error. It's just the raw difference between the true value and what we measured. So in this case, 9.2 minus 10 gives us an absolute error of negative 0.8 volts. Easy enough.
But an absolute error of 0.8 volts doesn't really tell the whole story. To get its real significance, we need the percentage error. By dividing that absolute error by the true value, we can see that our measurement is off by a pretty significant 8%. Now that gives us some context.
And from there, we can state the relative accuracy. If our error is 8%, that means our measurement is 92% accurate. This number right here is what matters in a professional report. It's the percentage of truth that our measurement actually managed to capture.
Now, these basic calculations are just the beginning. In a truly professional setting, you'll be using a whole toolkit. Things like the arithmetic mean of multiple readings, the standard deviation to understand the spread, and limiting errors to define the manufacturer's guaranteed accuracy. This is what separates a guess from a professional analysis.
So we're right back where we started with that one fundamental question. Can you trust the number your instrument gives you?
The difference is, now you have the foundational tools to not just answer that question, but to prove it. The power to validate your data, that is now in your hands.